So today I want to talk briefly about how quantum computers work behind, sort of behind the scenes, and what are some technologies that are involved in quantum computing. First, I mean, there's the critical, the most important component of the quantum computer, sort of, and this is the quantum part, right? Where does the quantum come from in a quantum computer? In classical computer, we have bits, zeros and ones. And then when we move to quantum, we have still zeros and ones. But besides the 0 and 1, we also have certain probability attached to both 0 and 1. So when we measure the quantum bit, there is a 60% chance that we measure a 0, and there's a 40% chance that we measure a 1, for example. And then the operations, they're not like flipping the switch, going from 0 to 1, but they're really like more like pushing a slider towards 1 or towards 0 and adjusting this probability that we measure either 0 and 1. How do we implement this in real world? How does this work? Well, there's essentially two main classes sort of quantum computers, and those are gate-based quantum computers, where we really want to do this adjusting of probability on a single entity. And then there's the second part, where we look at a group of such quantum bits and we adjust these probabilities for all of them at the same time. So we don't care about individuals anymore, but we care more about the system. And these are called quantum annealers. So let me start by saying some words about quantum annealers and how they're implemented and how we use them. Well, the main idea of quantum annealers is that we take a large set of particles, of quantum particles, and we connect them. We put them on a grid. And we know very well how to manipulate such sets of particles. We know how to evolve them. We know how to change electromagnetic field in certain areas. We know how to measure them. We know how to design it. Don't get me wrong, it's still a huge technological challenge to do it. But we can sort of handle larger sets of such particles. Why is this useful? Well, it turns out that in real world, problems can often very well be mapped to grids. So for example, you want to go from point A to point B in a city. You'll probably have to drive there. So you will drive down a street, there will be an intersection, then you will drive down a different street, there will be another intersection, and so on. Right? And if you want to find the optimal path, sort of the traveling salesman problem, it makes sense to think of this road network as a grid and then try to optimize for time or for fuel consumption or whatever you want to optimize for. And this is exactly what we do. So we translate real-world problems, mostly in optimization, into grid-based problems. And then we put them on annealers. So we initialize the grid of quantum states, and then we put some potential on it, and we let it evolve and see how the particles will sort of align. And then when we get the optimal solution, we then translate it back to a real world problem. So in essence, we're doing sort of a simulation. Instead of just going down all the paths, we do this on a quantum computer, which is much faster, and then we translate it back. And this approach, it's proven to be very, very effective in solving optimization problems. At the same time, because these interactions, we don't need to manipulate individual qubits or quantum bits. We can build much bigger systems. And quantum annealers today, they have like 5,000, maybe over 10,000 of qubits already. And they're extremely efficient in solving optimization problems. Now, going to gate-based quantum computers. Right? In gate-based quantum computing, essentially, what we want to do is we want to mimic sort of the prototype quantum system. And this is an atom. And the way atom is sort of constructed is that it has a core, it has protons, it has neutrons and the core. And then there's an electrons, or there's electrons that circle around the core. And the key feature, the key quantum feature that appears in such systems, because they're very small, is that if we want to move this electron, which circles around the core, further away, we cannot do this arbitrarily. So you cannot just change the radius by a little bit, but you have to change the radius discretely. And I mean, this is a very fascinating feature. It's a very fascinating feature of quantum mechanics. But it essentially has to do with the size of the smallest energy packet. There is the smallest energy that's available. And this is why when we're close to such energies, adding the smallest energy packet will actually discretely change the radius. And now if we look at the first orbit and the second orbit, and we label this one by 0, we label this one by 1, there is naturally a probability attached to this, which is, if we measure the electron, are we going to find it in the first orbit? Are we going to find it in the second orbit? And this is sort of the prototype system of a quantum bit, because we have 0, we have 1, the two orbits, and we have a certain probability of measuring the electron in each one of the orbits. And essentially all the gate-based quantum computers, they try to mimic this in some clever way. So the sort of old school way of constructing quantum computers is essentially this. So we take an atom, we take typically ions, and then we fix them, in space. We build more of them, and then we change their energies essentially. And by this, we change the probability that the electrons are in state 0 or that they're in state 1. Implementing gates on this computer, on this quantum computer, so implementing operations, especially operations that mix different atoms, can be challenging, because these atoms are not sort of naturally connected, right? We have to fix them in place, and then we have to design these connections. So this can be very challenging, but there's been a lot of progress made on this, and it's still being made. So the second implementation, which is probably the most common right now, is the superconducting quantum computers. And in this implementation, what we do is we build a circuit made out of superconductors. And it turns out that this circuit, if we design it in a smart way, it will behave exactly like the electron does in an atom. So it will have discrete energy levels, and we will be able to excite it to state 1 or de-excite it sort of to state 0. And these little circuits, they will form the qubits in the quantum computer. And here, especially building gates which connect different circuits, at least intuitively, it's simpler, because we just connect the two circuits, right? And then when we change one, the other one will change automatically, and we have some sort of power of manipulating this. Of course, in practice, still a very, very difficult problem, especially if we want this to be very reliable, as we do want it. But this is sort of the most common approach to building quantum computers right now. And then the third area is just building systems that behave like electrons in an atom, right? And this can, for example, be for topological quantum computers. We can have some phases of matter that exhibit some excitations, and these excitations might look very much like an electron does in an atom. So they have discrete energies, they interact with each other. We can do operations, we can change the probabilities of these excitations, right? And very interestingly, also the light, it can behave like a quantum particle. So it can have some states we can build, so from light, states that mimic quantum bits, or they mimic electrons in an atom. And that's also a very active area of research and very active area of development. This second part, so the gate-based quantum computers, they're typically smaller because we really want to manipulate individual qubits, and this turns out to be a very, very difficult problems, and there's errors associated to it. We have to keep this at very low temperatures to have superconductivity. There's coupling to environment, or all of those factors. They make these systems more difficult to scale than for quantum annealers. But there's a lot of progress that's being done. It's difficult to say right now which technology is ultimately going to be the one, which one is going to prevail. Maybe there will be more of them. But I am very excited to follow the developments, and I'm very excited to see where sort of the hardware of quantum computing is going to develop.